Switch performance troubleshooting. When I initially got into network consulting, one of the first jobs I had was a voice over IP conversion. And I got to the site to do a network audit, and I literally walked into racks and racks and racks of 100 megabit per second hubs. Now, mind you, this was 12 years ago, so it wasn't radically like what is going on here, but it was still at an age where it was very unusual to see that many hubs and at least as large of a network as they had here. And I told the guy as soon as I saw him, I go, whoa, these got to go. We got to replace all these things with switches. And he goes, no. He goes, I keep these hubs here because they are faster than switches. And for some reason that statement echoes in my mind. Because it stunned me. I was staring at him. I go, faster than switches. I said, why do you think that? And he said, well, just look at the OSI layer. Essentially, the hubs sit down here at the physical layer of the OSI layer, where they just essentially send the network signals where they need to go. The switches sit at the data link layer, so they got to kind of process. They got to learn the MAC addresses and all that kind of stuff. And I was like, oh, okay. So I sat down with them and actually had same conversation I'm about to have with you, talking about the core components of a catalyst switch. So if you take this switch in modern day and break it apart, you essentially have the interface. I don't know why I'm outlining this. I just do. It's like when you doodle. You have the interfaces themselves where you connect the devices into the switch, and that's allowing them to communicate. They all bridge together on a backplane to where essentially that's the fabric or the connection between all of those ports. And then you have something in there called forwarding logic. That's what Cisco calls it. Most people call it ASICs, right? Application specific integrated circuitry. Essentially an invention that changed the world or revolutionized the world. Nowadays you see ASICs for everything. And what is ASICs? ASICs is essentially a chip that is geared for a very specific purpose. It doesn't do much, but what it does very well and very fast. You see ASICs in video cards. You see ASICs to mine Bitcoin nowadays. You see ASICs to run your switches, which are able to make those forwarding decisions, that forward logic, at wire speed. That's one of the big difference between them. Now, back in the day, when switches were called bridges, they had like 4 ports, and you would connect your hubs to them, and they were software based, and essentially they would learn the MAC address on each one of these ports, and it would slow down as things went through them. But with the invention of ASICs, switches became one of those things that just flooded the market, because now you get the intelligence plus the speed, essentially wire speed. Now, when you're thinking about your switches, almost never will you overload the backplane. I'm sure there's some case in Cisco's archives where somebody took a 6513 switch, filled every single blade with 48 port, gigabit, or even nowadays 10 gigabit ports, and max this thing out to where literally the backplane of the switch became a bottleneck. But it would be a rare exception to see a backplane bottleneck in a device. Where you most of the time will see the bottleneck, and this is rare as well, but it does happen, is in the ASICs. It is possible to overload the ASICs, and the main reason it happens is because somebody is using a switch that is not designed for the kind of scale they're throwing at it. Like you've got your 3550 switch that maybe has become the hub of 1,000 user or 1,000 device network, to where essentially Cisco would scale you into a 4500 or 6500, even Nexus level equipment, but you're like, no, I can stretch my 3550. That's where you start seeing the ASICs get overrun, and that's when bad things happen. I'll tell you what can happen in just a moment. The last piece of this is the control plane. You can think of this switch, if you were to divide it into a 2-layer cake, right? You've got the data plane down below, which is governed by the ASICs, right? that sit down there. That's where your ports are coming in. It has all the MAC addresses that it reads them. It figures out where it's going to go and then sends it out the other ports. That's all happening down below. Now, in layer 3 switches, you have this thing called a TCAM table, where previously, layer 2 switches, you only had a CAM table, content accessible memory. It's where it stored all the MAC addresses. TCAM is ternary content accessible memory, or layer 3 essentially information that the ASICs are now geared to handle basic routing functions, which makes these things formidable when it comes to speed of routing, to where they can actually do routing at wire speed, which is why, man, I'm talking fast. I just have a lot to share with you, my friends. That's why nowadays with our network design, we're like, VLAN it off. Throw a VLAN over here and over there. And you want, 2 devices on that VLAN? That's okay. We can do that because you've got TCAM and you have ASICs powering this thing to where you can do that crazy routing at wire speed, right? So above the data plane, where I was going with this, is you have the control plane. That's all right. Minor road bump. Control plane is where all of the intelligence of your switch resides. So when you telnet in, or SSH in, or user routing protocol, or Cisco discovery protocol, or first hop redundancy protocols like HSRP or VRP, essentially anything that requires some thought, if you're thinking like a switch, and there's no ASIC designed to handle it, that's going to be sitting up here at the control plane. You have to protect that thing. That's why there's a whole security section around the control plane. When you're thinking about protecting your switch, you want to make sure that you isolate SSH access or telnet access, not just because somebody can get in and try and hack your password. It's just those provide open ports to the control plane where somebody can just start hammering that thing with TCP requests or something, causing your processor to spike on the device. So the control plane is something that we must guard. So now we're thinking about performance issues with these devices. Where can they happen? The 2 most common issues that you can have performance-wise on a switch are port errors and duplex mismatches. That's essentially at the core of it. And this leads to the dreaded, the network is slow comment, or things just feel slow. It's just difficult to handle those kind of statements, which they're 100% valid, but it's like it could be anything. So you really have to start narrowing down where would that slowness come in. On the switch side of it, the quick way to diagnose slowness issues is to do a show interfaces counters. This gives you a quick view of what interfaces are doing what, so you're able to quickly see relative to each other how many input packets, unicast packets, you can see multicast packets, broadcast packets are coming into these interfaces. And then you can scroll down and you'll be able to see the output, unicast, broadcast, multicast packets that are going from the interfaces. So that's a quick way if you're trying to say, okay, is my switch being flooded with data? We can quickly find ports that are way out of whack, at least from a counter perspective, by doing this. You also can tack on the command show interface counters errors. This shows all of the error statistics for the interfaces, so I'm quickly able to see if there's any alignment errors or frame check sequence errors or transmit receive errors. The errors will typically come in, these guys right here, are usually going to happen because there's some kind of bad cable, bad interface, bad transceivers. Yeah, I don't know if you've seen these things. These things, transceivers are death. These things have caused so many issues where essentially fiber optic cabling was run at a time where fiber interfaces were either unavailable or too expensive for the customer. So what they do is they buy these little transceivers, which are really just, they look like really cheap devices usually. It has a fiber interface in and then an Ethernet interface out, and it does something like this. Usually has a little plug that somebody's jacked into the wall. I've just seen way too many of these things go haywire to where they just start spazzing and causing performance issues all around the board. But they rarely, I won't say rarely, but they usually go into that half-life state to where they're causing all kind of performance issues, but they just don't die. You wish they would, because then you're like, oh, there's an outage. Oh, it's the transceiver. We should get rid of that thing. But instead, it's kind of like, ugh. So a lot of times doing these commands like show interface counters and being able to see which ones are just filling with errors will help you out a bunch. The second cause of performance issues, or I should say the main cause of performance issues, are duplex mismatches. Here's the fact. When you have a device and you set one side to auto and then you hard code the other side, let's just say the server's hard coded to 100 megabit per second full duplex, you're always going to get a duplex mismatch because the Ethernet standard says if the auto side is unable to detect what the other side is, which it can't if you've hard coded. In order for auto detect to work successfully, both sides have to be configured for auto, right? So if it can't detect what the other side is, then it's going to default back to half duplex because that's what most things ran back when this auto detect Ethernet standard was developed, right? Well, here we are, fast forward to year 2015 and beyond, right? It's like, come on, let's get out of that world, but it still happens all the time. I mean, the fact is, the mean time between failure on switches, I mean, I've seen these things run for 10 years more, you know, that these things just keep on chugging. 100 megabit per second still works just fine for a lot of organization, so they keep them around, and you still run into this auto duplex thing. That's where, and this kind of combines with one of the other nuggets where I was talking about filtering commands. It's where the filtering commands can come in so handy. You can do a show interfaces, right? And that'll show you real quick. That's my VLAN one. I can go, okay, that one's set up for auto. Doesn't look like anything's happening there. Okay, this one's full duplex, 100 megabit per second. I mean, that's cool and all, but you know, it's going to take a long time to scroll through a whole bunch of switches with a whole bunch of ports and say, okay, is that auto? Is that auto? That's where that filtering command comes in, where you can just say, show me the interfaces, you know, give me a quick include line protocol, and we'll do a duplex as the second line, right? You're able to quickly see then, okay, I can just scroll down, this guy's down, up, and I can see just going down, okay, full, auto, full, etc., etc. Something you might do, and it wouldn't be too hard to create a script for this or a program that could check in on it, to where you would do something like show interface, include half, right? If you just want to, oh, take a look at that. Hey, what a great example. We've got a half duplex interface somewhere in there. Now, I don't know off the top of my head a command that would do it to find it. Oh, that right there. Fast Ethernet 2/0. So I'm trying to think. There, I'm sure if we sat here long enough and thought it through, we could create a command that used these filter things to show what interface it is and having half underneath there, right? But nonetheless, that's one of the things you want to be able to find in your network, because that's a misconfigured device most likely. One more thing to mention before we get into the TCAM troubleshooting, and that is auto, speed, and duplex. It's always been my mantra that I have said, you auto, not use it. And that's because 100 megabit per second switches have ruled the world. And there's still a ton of them out there, so I'm not saying that mantra has changed. However, if you have gigabit everywhere, you want to stick with auto, because essentially the algorithm is fixed, and as long as you have gigabit switches all over the place, it's going to detect just fine. And I mention that because there is one feature called Auto MDIX, which requires you to have auto, speed, and duplex enabled. It is media dependent interface crossover. Essentially, this is what allows you to connect your switches with whatever kind of cable you want instead of needing crossover and straight through. Essentially, Auto MDIX allows it to detect which ports are actively being used and flip around accordingly. But in order to use this, you have to have the auto detect mechanism turned on. So, enough on that. Now let's talk about TCAM troubleshooting. TCAM being the ternary cam, or essentially ASIC-based layer 3 processing of a switch. The switch backplanes, as I mentioned on the previous slide, rarely cause an issue. Cisco does a great job about equipping their devices to where it can handle the number of ports it has, where they're essentially all maxed out, right? They're all sending and receiving at max capacity. However, the TCAM tables can max out. That is the ASICs of the device. Now, when the TCAM table is full, the traffic will go straight to the CPU. That's why I put this little picture right here. Essentially, when it comes to the switches, it's got ASICs to handle just about everything, but the CPU is this little guy. It's not meant to be a huge processing kind of device, because it's kind of like, you know, I don't know why this popped in my head. Iron Man. Have you ever seen that movie where who's that? Robert De Niro, Robert Downey. Anyway, the guy who is in the Iron Man suit. He's, you know, and somewhere in some country a grenade blows him up. He can barely walk, all that kind of stuff. So he creates this essentially armored suit that he goes around and you got to see the original one. It's awesome. So anyway, this is like the iron suit, right? The ASICs. The CPU is like the little guy inside who's all injured with grenade shrapnel and all that kind of stuff. That's your switch without the grenade, right? So it's not designed to handle all of the processing, but that's exactly what happens. It's called punting. You'll actually see a line on the switch where it starts punting traffic to the CPU when the ASICs are maxed out or the TCAM table is full. Now, how does the TCAM table get full? Well, essentially you overutilize the switch. Essentially, switch death, I'm saying, can occur when you use a low-end switch in the place of a high-end switch to save money. Essentially, you're taking something that was never designed to be in the place that you have it, and you're seeing if it works, you know, to try and cut budgets or whatever the case is. And can I mention, this is something that, well, at least frugal IT people do all the time. And I'll put myself right in there. I'm one of those guys that's like, I'm on eBay trying to save money, all that kind of stuff, right? And you're like, yeah, why don't we just, you know, we can use a 3550 as the core, right? It should work out. And you kind of see if it works. And if it can, you're like hero of the day because you did a network upgrade. But the fact is, you know what? When the network's down, nobody remembers that you saved them $10,000. They're like, get it up now. What are you thinking? Why didn't you know? I mean, all the people that are your friends turn on you so quickly. Friends, So anyway, that's what can happen when you overrun the switch. But punting is a normal condition. I want to come back to this. So don't do show commands on your switch. You're like, oh no, I see punting, because essentially anything that requires access to that control plane is considered a punt. It's when you see that punt count starts skyrocketing and the processor utilization getting pegged that you have a major problem. So, first thing to do before we start, you know, when we're looking at how do we make sure that our switches are optimized, make sure the right SDM template is in place for those required features. What is that? Well, most stackable switches out of the box are designed by Cisco to do a variety of things. Like I've got a 3750 sitting right here. I'm logging in. I'm going to type in show SDM prefer, which is essentially what template is applied to this switch for its functionality. Out of the box, a 3750 per Cisco is using desktop default. What do they mean? They mean they design this thing like an access layer switch. It can do routing because I can see right here that it's got IPv4 capability, 1,000 kilobytes, or essentially 1 kilobyte or 1,000 bytes to store IPv4 IGMP groups, 8,000 bytes to store unicast routes. So you can see it can do routing, but really the lion's share is designed to hold MAC addresses. It's like, hey, I'm here to have a cam table that dreams are made of. You can change the template around. You can see it supports an access bias, and you can say, well, show me what that one is, and you can see that the access bias skews the numbers a little bit. It says, okay, well, what about a routing bias? And you can see all the numbers kind of move around. You notice the MAC addresses go lower and the IPv4 routes go higher. They allow you to do policy-based routing, whereas typically they don't even allow policy-based routing. This is something to know, by the way. A lot of people have spent a lot of time troubleshooting policy-based routing because it's just not working even though it takes the commands. It's because the resources haven't been allocated via SDM template in order for this switch to do it. So all you got to do to change the template is go into global config mode and do SDM prefer and choose whatever template that you want. But no, this is something to do when you originally set it up, because it will require you to reboot your switch, because it completely changes the way the TCAM allocation works, right? If you ever want to see your TCAM utilization and say, okay, am I approaching it? Am I getting there? You can do a show platform TCAM utilization. And that will give you, essentially, based on your SDM template, what are the max and minimum values you can have for each one of these. And they're saying masks and values. And this is how ASICs works with it. I mean, really, ASICs are dealing with ones and zeros, right? Down binary code. And they do it through this thing called masks and values. There's a whole bunch of reading you can do on that if you're really interested in it. Over here it shows what's used, but again, Cisco's like, hey, this is complex. This is kind of like an estimate that you can't really like say, hey, well, my switch has 6,200, unicast MAC address values that it can contain. While it could be relatively close, really they're like, hey, this is just kind of an abstracted view of what this SDM template can do. Now let's look at the processor itself. Essentially, CPU utilization matters on the switch. It should remain low. Essentially, it is Iron Man, right? It's got this suit that can handle everything. That's what the ASICs are designed for. So Cisco recommends a maximum of 5 to 10% on your CPU, which I know if you're used to a router, you're like, seriously? Yeah, seriously. Low is better. If you're going above 10%, Cisco themselves considers that abnormal. That's how much they depend on the ASIC. So don't immediately assume that you've overwhelmed your switch and you got to go buy a bigger one. First thing you want to do is do some investigation. Check that TCAM table. Am I overloading it to where it's punting a whole bunch of traffic to the processor? Or sometimes if you've got like a spanning tree loop going on. Essentially, our ASICs are that good nowadays that you can have a loop sometimes and not even know it, because the ASICs are handling all that, but essentially they're holding on by a thread. So check your interface counters. Do you have one going through the roof? You'll see status messages via syslog, like MAC addresses jumping between ports, and the switch is like, help me, help me. So always pay attention to your logging. Maybe you have a debug command left running. I've done that so many times, where you're doing some analysis, you've got a debug, and you just kind of walk away from the console port with that debug turned on. Debug causes high CPU, so make sure you do a uall. That's the undebug all command to turn them all off. Do you have frequent routing or FHRP updates? I mean, sub-second convergence is awesome. So you tuned your hello timer way down on OSPF or EIGRP or HSRP, right? And that is great to be able to converge that fast, but make sure your switch platform can handle these hello, these millisecond hello timers. Because that will cause the processor to go up, because it has to look at each one of those, reset dead timers, all of that. Lastly is frequent SNMP scans. When you're monitoring via SolarWinds or PRTG or something like that, to where it's looking at the different interfaces, how often are you checking in? I've seen people set it to once every 5 seconds, which means every 5 seconds you've got an SNMP management station scanning all these ports, and that can cause your CPU utilization to spike as well. So verify all of those things before you make any big moves of changing switch platforms. While they can do a lot, switches are unbelievably simple devices at the end of the day, so that is the core of your switch performance troubleshooting. I hope this has been informative for you, and I'd like to thank you for viewing.